Can people on Zoom hear me? Anyone on Zoom? Hello? Can people on Zoom hear me? Okay, great. Hmm. Guys, okay. Okay, that was interesting.
Question about hash maps, like before the lecture starts? Or...
Sure. What's up?
One question about the hash map. It's similar to that of like virtual pages in type 6.c, right? Like the way it's coded, or it's not really like that.
Well, virtual pages is more like circuit based. Like it's actually like built in.
I beg your pardon?
There's going to be more like hardware with the virtual page system, right? Because virtual page system isn't like it isn't just software. It also has like some hardware components to it. So you do have some slight differences there. I will say that it's similar in a way, right? I can think of a virtual page system as a map from physical pages to virtual pages.
I was more into hardware than software. So like the stuff I learned about hardware, I learned it first compared to like learning data structures. So I wasn't sure.
Yeah, I mean, I would say that's more consistent with like the concept of a map than the concept of a hash map.
Yeah. Okay, thank you so much.
Sure. Huh?
Like similarly coded for like a hash map, or
well, like I said, where the hash map is like purely software, whereas the virtual tables it has like some hardware components associated with it. So I don't really say that it's like coded in the same sense. Yeah. All right. Good afternoon. How's everyone doing? Good. Welcome back. Welcome back to this class. How's your spring break? Did well? Poorly? All right. We got a few things coming up this week. So first off, Project 2B is going to be due this Friday. Make sure you get on that. Homework 3 is also going to be due this Friday. Now, it is a midterm 2 review homework, so it is considered within scope for the midterm, which is on Wednesday. And it is going to be very helpful to finish it before the midterm. We're just putting it to be due on Friday just because like the schedule ended up acting weirdly. We didn't want to have an assignment due immediately when you get back from break. In particular, there is one question, I think our question 2, which covers some new content that we added this semester, which will be on the midterm. So make sure you complete at least question 2 on the homework. And you can read more about it on Ed. We have a post describing exactly what's going on with that. Our midterm is this Wednesday. How do people feel about that? Good, bad? How many people say it's bad? How many people say it's good? Yeah, that's what I kind of figured. Sorry, this is kind of how the schedule just turned out. We couldn't find rooms at another time. There was someone asking if we could do a midterm review session on Wednesday. So I do have an idea for this. So I'm going to put it up to a vote once I explain what we can do. So for Wednesday's lecture, option 1 is we just do it as normal. It's going to be on prefix operations and tries. We'll be just kind of doing it as usual. Option 2, I'm going to spend about the first 30 minutes talking about tries, and then I'll take 30 minutes to do midterm review. However, I'm not going to be able to cover everything about tries that I would like to cover. So you will have to go on your own and watch the pre-recordings that I think Josh puts up every lecture. So we won't have a full lecture on tries. You will be still expected to have like the full knowledge of it. We do have alternate videos that you can watch instead. But in exchange, you will get 30 minutes of midterm review on Wednesday, right before the midterm. So does anyone have any questions on those two options? All right. So just as a quick vote, how many people would prefer option one? We just go through lecture normally. Okay. How many people prefer option two? 30 minutes of prep. All right. This is about even. This was not helpful. All right. All right. Show of hands for option one again. Well, 16, 17. All right. Option two. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. All right, it's about 18 to 30. So we are going to do option two. We're going to have a midterm review during Wednesday's lecture. All right. Are there any specific topics you want me to cover on midterm review then? Yeah. Asymptotics? Just asymptotics? Yeah. Heaps? Yeah. Heaps, yeah. LRBs? Weighted coherence? All right. Sounds, yeah. Graph traversals or tree traversals? Both. Both types of traversals. All right. Seems like we have a few things to cover on that. All right. I'll get that set up. All right. So just as a heads up, I was sick over the weekend, so I didn't prep this lecture fully. Just be aware, if I mess stuff up, there are alternate videos you can watch instead. All right. So today's lecture, we're going to be focusing on a very specific type of graph. It's called directed acyclic graphs. And while we are focusing on this, our more general goal here is to kind of get some practice on more of these A-level problem-solving skills. Kind of, can you come up with a solution to a problem that you're given? So just as a quick overview, here are kind of the problems that we've solved with graphs so far. We have the paths problem, which was just trying to find a particular path from a starting point to every reachable vertex. The shortest paths, back when we didn't have weights, we could solve it with the breadth first search. Once we added weights, we had to use something like Dijkstra's or A star to get an actual shortest path. We also discussed the minimum spanning tree problem, where your goal is to come up with a tree that connects every single vertex and which has the minimum total weight. And we found a number of different solutions. Prims and Kruskal's were the two big ones. And we found that we had E log V and E log E time, which is effectively linear in the number of edges. You have a log term, but that's going to be relatively small. Today, we're going to actually come up to a new problem. So this problem is the topological sort. Let's say that you have a graph. It's specifically a directed graph. And this graph represents tasks, right? So A is a task, D is a task. And the idea is that we put an arrow if there's a dependency between the two. So you need to finish A before you finish D. For example, if you're cooking something, right? A might be buy potatoes, and D might be peel potatoes, right? You need to buy the potatoes before you can peel the potatoes. So there's this dependency. And your goal here is to kind of write some order of these nodes such that you finish all of the dependencies before you finish each task. So what algorithm can you come up with that, given an arbitrary graph, tells you what the order is? And even if there exists an order at all. So let's take a few minutes to discuss this with your neighbors. Try and come up with an algorithm for this. This one's fairly tricky, uh, but feel free to try and work with your neighbor on this. Let's take at least 3 minutes on this. All right. Let's bring everyone back. What did everyone come up with? Anyone have an idea on how to solve this problem? Yeah.
So find all the roots of the graph, remove those, and then do that again until there's no more elements.
Okay. So you start off by finding all the roots, which I'm assuming you mean nodes which do not contain any edges going into them. Yeah. You remove them, and then you just repeat until the graph is empty.
Yeah, and then you add each time you add the roots to like I guess the list.
Yeah, you have some lists that you keep track of them. What would be the runtime for that?
Um, oh, but it's you could just leave it like
O of n. Is that true? Does anyone have another answer for that? Why is it worse than that?
you gotta go through nodes and the edges, no?
Yeah. So first off, how do you determine what nodes are roots? Yeah. The easiest way to do that is to go over every single edge. That takes O of E time to finish. And then you need to do that potentially up to V total iterations. So that's going to be E times V in the worst case. That might be a really bad bound, but at the very least, it's somewhere around there. Can we do better? Does anyone have an improvement to that idea? Yeah?
Maybe think of it as n factorial,
N factorial?
or where we go to the first n, then n minus one, the n minus two, and such.
Well, N factorial is going to be significantly worse than V times E, I think.
Yeah.
But, and I'm not sure where you're multiplying things together. Can you do better? You can, yes, because I'm asking this question. So how do you do better? Yeah?
Like perhaps you can like keep track of which which nodes the the roots that you were pointing at, and you say that those are the ones that like those are the only ones that could potentially be used after you move over.
Yeah. So as an improvement to your approach, one thing we could do is keep track of the nodes that we remove, right? And look at all the things that they're pointing to, and then kind of count out how many edges are pointing to those, and then decrease them until they get down to zero. Yeah. That is a good approach. Using a heap, for example, you might be able to decrement. You kind of like insert all the nodes with their value being the number of edges pointing into them, and then you just remove items and decrement, updating the priorities. I believe if you do that, you should be able to get uh, something similar to V plus E log E runtime. Yeah, something like that. I don't exactly remember fully, but it would be a similar runtime to Dijkstra's, which is E log E-ish. So you can do that. Can we do even better? So this one's actually really tricky. The vlog E solution is kind of like what I would consider to be the most natural approach, or the one that you get after you kind of optimize out like your first idea. The solution that we've come up with is actually going to be even faster than that. I believe it's V plus E. And the idea is you just perform a DFS. You perform a DFS, uh, but you run a DFS post order, and then you reverse it. Now, if it doesn't make sense kind of how this works, let's just go through an example first, and I'll kind of explain why this ends up working. So let's just go through an example of how this might happen in practice, right? So, yeah.
What is it that would be by what do you mean by topological sort?
A topological sort? A topological sort is just an ordering of these such that every single node, if it's pointing to another node, like say A and B, right? Then A comes before B, B comes before E, and so on. Yeah.
Same as a natural order.
It's not the same as a natural ordering. It depends on what you mean by natural ordering.
So the thing that comes after is less than the thing that comes before it.
Yeah, so one way you can think about this graph is that these represent like less than and greater than in like a partial ordering of this. And in that case, it would match what you mean by natural ordering. But there can be multiple distinct topological sorts associated with the same set of data.
For example, I'm noticing that the valid orderings are not what we call natural, but those are still topological.
Yeah, these are still topological sorts because if you look here, A and D, right? There's an arrow from A to D. A is always before D, regardless of which one we're working in, and so on for every single one of these arrows. As long as you have an ordering of this, that is considered to be a topological sort. Yeah. So multiple topological sorts can exist even if there exists like some natural way to order things within the given data set. Like letters have a natural ordering to them. We're not talking about that because those are just like labels. Yeah. So let's kind of go over a demonstration of how this would work, and then we'll kind of go into explaining why this works. So first off, I'm going to start a DFS on a random node that has 0 in degree. Which one do you want to work with? A or C? A? Yeah, because A looks like the smallest letter. Let's start with A. If I do a depth first search, what do I look at next? Let's say that I always tie break by alphabetically. Yeah, I'll look at B. Here's my call stack. What next? E. All right, what next? H. Now H doesn't have anything left. So now I just go back. So the H gets added to my post order. Then E gets added. Then B. Then A doesn't get added yet because I still have some children. So what do I look at next? D. So now I have the call stack D. D doesn't have any further children to look at. So I'm done with there. And then I come back to A, A doesn't have any further children, and I'm done with this depth first search. Now, what do I look at next? C, yeah, and then F, and then G. G is done, so we add G to the list. Then we add F to the list. Then we add C to the list. And then if I just take this and I reverse the order, then I get this sequence C, F, G, A, D, B, E, H. And I can do a confirmation to show that this is indeed a topological sort of this. Now, the reason why it's called a topological sort is that we can kind of think of this process sorting these nodes so that they appear in an order that's consistent with these edges. So if I kind of sort off these nodes in the CFG, ADB, EH order, then it kind of forms this version of the graph where all the edges are pointing right. So we're kind of sorting these nodes so that all the edges point right. So let's talk about why this works. So does anyone have an argument for why this would work all the time? Well, let's start off with this. Since we're reversing this list, right? This is kind of saying that the reverse of this original order, it should always have nodes that are pointing to something before the node that points after. So in order to ensure that A comes before B, A comes before D, etc., on this topological sort, once we do the DFS post order, we should expect that B is before A, E is before B, D is before A, and so on. Kind of the opposite because we're reversing it after. So is this always true? Within a single grouping here, right? Let's assume first that there's only one of these sources. Is it true that the source is always going to be the last thing put in? Yeah. Why is that? Yeah. Yeah, because the post order is always going to be visiting all the children before it visits the current. Yeah. In effect, this A, it's definitely going to come after all the things that A can eventually point to. From here, right, this D, does it come before everything that it points to? Yeah. The same way that A must come before everything that it points to, D must come before everything that it points to in that same way. So in the exact same way, it's kind of because DFS is kind of recursive, every single node within a given set of these ends up in the right order. You end up having A come last, and then all the things that only come before A must come later. Now, if you have two of these paths, like say you have two of these sources, is it true that the order of these doesn't really matter? Why?
Because as long as the stuff always comes before the current source, and since the current sources have no order between each other, then you can just do the first source first, and those will always come before the first source, and then the second source, and then those will naturally always be before the second source.
Yeah.
Later.
Yeah. So if you look at A and C, there's kind of like three sets of nodes, right? We have the nodes that both A and C go towards. We have the nodes that only C goes towards, and we have the nodes that only A goes towards. And if you look at each set, you can see that they always occur before the corresponding A or C. For the F and G, they come before the C because we went through a DFS post order on this. For everything that's shared, it came before the A because it was within the A's post order traversal. And it comes before the C because we already dealt with everything in this post order traversal before we moved on to C's post order traversal. And for the B, that came before the A because it was within A's post order traversal. So every node kind of ends up before everything that needs to be before. So any questions on that? I know that's kind of a hand wavy explanation. If you want to discuss with me in office hours later, I can present a more formalized proof. All right. Now, just as a warning, when people say depth first search, they sometimes mean that you do a search with restarts and sometimes without. This is kind of just like kind of an overloading of the term. You kind of use whichever one is more relevant to you in the given time. So, for example, when we were doing the depth first paths, we were just looking for reachability. We didn't need to restart ever. Because we're only looking for the ones connected to the starting point. Topological sort, we actually just wanted to restart every time we ran out of vertices to look at. And because of that, we are using a slightly different definition of depth first search here. Now, what's the runtime of this algorithm? Well, in order to do that, we need to first figure out the runtime to find all the vertices of degree 0. As we mentioned, it could be done in theta e time. You just look at all the edges. You kind of count out how many times you see an arrow pointing to a particular node. But interestingly enough, you don't actually need to do that. If you look at the topological sort algorithm, you might notice that it actually doesn't need to start the post order from a node whose vertex has in degree 0. It can start at any arbitrary node. And the idea is, as long as you look at the like sources of a particular node later, the properties of this topological sort are still going to hold, right? If you start off a post-order traversal at this node and look at all of its children, and then later look at this node, then this node is going to be placed later than the entirety of all these children. So that means in the reverse topological sort, this thing is going to be before all of these children. So it doesn't matter that you actually start in an in degree 0 node. You can just pick an arbitrary vertex and just keep doing that until you mark all the vertices. And if you use this, then you should be able to get a runtime of V plus E. So let's test your understanding. Give me a topological sort for this graph here. Let's take a minute on this.
Oh, actually,
All right, let's bring everyone back. Can someone shout out a topological ordering for this? ADB, CEF? Yep, that seems like a reasonable topological ordering. Is that the only topological ordering? Yes, because there's this chain ADBCEF where there's arrows between each one. There's no way to change that path. So there's exactly one topological sort for this. That's not necessarily true for all graphs. Now, one final note here is that a topological sort will only exist if the graph is directed and acyclic. So a directed graph is one which has arrows. We don't really have a concept of a topological sort if you have an undirected graph, because you don't have the concept of something must come before something. And it must be acyclic, which means that there's no way to go from one node back to itself. For example, like here, you have a node A to B to E to H and back to A. Like if you imagine you have two tasks, right? Task A requires you to have task B done. Task B requires you to have task A done. It's impossible to complete either one. So you're not going to be able to get a topological sort in that case. So as it turns out, topological sorts tend to be very useful. Directed acyclic graphs tend to appear in a lot of real-world things. For example, your classes form a directed acyclic graph, we hope. Because you can imagine that you have nodes representing your classes, and then prerequisites being the arrows. And ideally, you have it directed acyclic because otherwise there are classes that no one can ever take. Yeah. And as it turns out, if you restrict graph algorithms to work only on directed acyclic graphs, you can actually solve some things that can't be solved on general graphs, at least as far as we know yet. So let's take a look at this. So let's come back to the shortest paths problem that we talked about for general graphs. And let's look at how it changes when we look at directed acyclic graphs. So first off, what is shortest paths tree for this graph? How will Dijkstra's tell us the shortest paths tree? Well, what happens first? We mark A. A connects first to what? B? Yeah, because B has distance 1 from A. What do we look at next? Huh? D? Yeah, because this is distance 2 away. This is currently distance 7 away. What do we look at next? Yeah, we look at E because this is distance 5 away. This one's still distance 7 away. What do we look at next? F because this is distance 6 away. And then C because that's the last one we have left. So if we do this, then we should end up getting our shortest paths tree. Now, what order do we visit these nodes? A, B, D, E, F, C. Now, if we allow negative edge weights, Dijkstra's can sometimes fail. You can see here an example of when this would fail. For example, if you look here, the shortest path from A to E would be taking A to B to C to E, which would be negative 13 distance. But we don't notice that because we've already assumed that we found the fastest path with going to E. In effect, the relaxation on E is going to succeed, but because anything further doesn't get updated, the distance to F is never going to be updated. So we end up not getting the perfect, the best paths for everything. So let's try to come up with the shortest path algorithm for a directed acyclic graph if there are negative edges. In effect, you should be trying to find an ordering which you can relax these edges so that you can still guarantee a correct shortest path for every node, even if there might be negative edge weights. Let's take a minute or so to figure that out. So keep in mind that this algorithm is only going to really work if you have a directed acyclic graph. You shouldn't be looking for a general solution because the general solution is not known. If you find an efficient solution for the general case, then it is going to be worth $1 million. So please tell me. I, I don't even need the money. I just want to know if it's possible. Anyway, did anyone come up with an idea on how to do this? Yeah?
Could it be naive to say we could just use the exact same thing, but then we don't necessarily care if the distance is less than 0 because everything's just relative now to something that has negative 20 in it?
Can you kind of explain what your idea is?
Because we just use something like Dijkstra's again, right? But then, because I remember we talked in the previous lecture, I was like, why can't we just add 20 to everything? Because that would mean that all of the things are now added. But if we just don't care at all about that, could we just say the negative 20 might make some of the distances, the pink distances negative, but that's okay. Just keep doing the algorithm.
Do the algorithm as normal? Well, we already showed here that if you try to do the algorithm as normal, then you are going to end up messing up, right? Here we can see that node F, the fastest path is going to be negative 12, but right now we're claiming that the fastest path is 3. Yeah. Yeah. Yes.
Can you, in graphs in general, manipulate the edges in any way as you go?
Can you manipulate the edges in any way? You could, but if you find the shortest paths of a new graph that you yourself created, you still haven't answered the original question of what is the shortest path in this original graph I gave you, right? If you took the absolute values, well, you'd have to prove to me that that would still yield the same shortest path. And I don't think it will necessarily yield the shortest paths the same. Yeah.
Maybe
consider the nodes that have either a negative pointing towards it or a negative pointing away from it, and then you try to go. You use red curve in both the forward and backwards direction to find to get to a point where it's no longer negative. I suppose like you say going backwards, for example, 6 that produces negative 14 for that specific path. You go forward 1. That becomes
kind of like combining paths. Yeah. That unfortunately can lead to exponential growth. And it's not even necessarily true that you're going to end up having paths in the first place. Like imagine if all of these edges were negative, right? So this doesn't quite work either. And it could yield to exponentially many edges. Well, because it's a directed acyclic graph, I did say that this only really works on a directed acyclic graph. And what is the only thing I've told you works on a directed acyclic graph, but nothing else? Topological sort? Yeah. So let's just topologically sort this. All right. And once we topologically sort this, I'm going to claim that the following algorithm is always going to work. We first find the shortest path from A to A, then from A to D, then from A to B, then from A to C, then from A to E, then from A to F. Kind of, we use this order to visit the nodes instead of the standard Dijkstra's approach of visiting closest nodes. And does this always work? Yes, why? Yeah, because we have a topological sort order, all of the nodes to the left have already been fully, we've already found the shortest path to them. There's no way for us to find a shorter path by looking at later nodes. The whole goal of Dijkstra's was to ensure that relaxation never succeeds on a node that we've already evaluated. And that's why we looked at things in order. And as it turns out with the directed acyclic graph, we can prove that we can't relax on an already looked at node if we look at nodes in this order as well, in a topological sort order, because no edges are ever going to go back to the left. So let's kind of look at an example. So once we've topologically sorted this, we're going to look at this. What's the fastest path from A to A? Just A to A, 0. The fastest path from A to D is what? There's only one path. It's the A to D. So what we're going to do is we're going to relax A, and we're going to give these values 1 each. We then go to D. We relax both of these. This yields a B value of what? 1 still, because 26 is worse than 1. What about on this side? 2. Then we look at B. B's current distance is 1. And then we move 6 units to C. How much distance is C now? 7. We look at C. C's distance to E is what? If we take the shortest path to C and then go to E, what's the distance to E? Negative 13. So we'll update this to negative 13 and we'll update this to 8. And then we'll look at E. Negative 13 plus 1 becomes negative 12. So we end up getting the path length of negative 12 there. And using this, we are going to be able to get the shortest paths from A to every single other node. Now, the total runtime of this is going to be V plus E. We don't even need the heap anymore because we're not sorting any items. We're just looking at each edge directly. So because of this, we end up getting not just an algorithm that's better in a sense that it can handle negative edge weights, but also is faster slightly, just because we're using only directed acyclic graphs here. So using a directed acyclic, if we can show that our graph is a directed acyclic graph, then we can find shortest paths much more efficiently than if you were to just do it on a general graph. Now, let me ask another question. Let me ask, how do you find the longest paths tree for a graph? Now, the path must be simple. I'm not going to let you just cycle around infinitely. So you can't just say I go A to B to D to E to G 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 to D indefinitely and get an arbitrarily large value. I'm going to say that each edge can only be used once. How can you solve this problem? As it turns out, it's really hard. The best known algorithm is exponential. And if you manage to solve this, then this is one of those $1,000,000 problems. If you solve this, then you are basically the greatest computer scientist this century. So this is kind of something you can do at a later time. Just try and think about why this is actually really hard. Try and figure out why this has stumped mathematicians for like so long. But as it turns out, if we restrict to only directed acyclic graphs, then this is a solvable problem. So let's do that. Let's try to find the longest paths tree for directed acyclic graphs. And let's take a minute to solve this. And as a hint, you don't actually need to create a new algorithm.
I was just thinking, it's just the same yeah. See how like I don't understand. Instead of one short of ones, well, we choose whichever one best to go this one. Otherwise, it's but A. People can find it.
All right, let's bring everyone back. Did anyone come up with an algorithm that can solve this? Yeah.
Make everything negative.
Make everything negative. Yeah? What happens if you make everything negative?
Use the old algorithm.
Yeah. If you just create a new graph where everything is negative, then all the longest paths turn into shortest paths. And we already have a directed acyclic graph shortest paths tree algorithm. So you can just use that directly. No need to do anything fancy. Just we've reduced this problem down to something that already exists. We've solved this problem already where you have shortest paths for negative edge weights. So just create a new graph and make it a shortest path tree problem. Now, there was a discussion here about how you can't just like change the graph randomly, right? The reason why this works is because we can show that the shortest path tree of the new graph is the same as the longest path tree of the old graph. So we kind of show that the solution that we come up with in the first smaller graph that we could work with is the same as the hard graph that we couldn't work with directly. So because of that, we can kind of create our own graph ourselves. Now, if you have a high degree of mathematical maturity, this should seem to be just correct immediately, right? Directed acyclic graph shortest path tree, they do work on negative edge weights. And we know that if you just negate everything, then you've turned everything from largest to smallest and vice versa. Now, this is kind of part of the CS curriculum here at Berkeley. And it is really important as computer scientists to have that kind of sense of numbers. It hasn't really been a major focus in 61B too much, but it definitely will be in other courses. 16A, 16B, 70, 170, all of them are going to grow your mathematical maturity quite a bit over time. Yeah.
For the previous problem, also initialize all the starting edges to be like negative infinity, and then just use the extra algorithm, but test that it's greater than the current weight.
Yeah, you could start everything at negative infinity and test if everything's greater, but that's effectively the same thing as running the Dijkstra's on negative edge weights equivalent. Well, iterating over everything and making it negative still takes v plus e time. It doesn't add any additional runtime operations. So I would say that it's kind of more elegant in this way to just use the pre-existing one, right? You don't want to like reinvent the wheel. But your way does. Does Dijkstra's work on negative edge weights? No. We kind of showed why this doesn't work on some other previous cases. Huh? Neither does A star. No. There is an algorithm that does work for some types of directed graphs called Bellman-Ford, which does work with some negative edge weights, but it's limited in some scopes as well. You'll learn more about that in 170. All right, here's some good exercises to try out later. Try to convince yourself why these problems are actually hard. Now, this is kind of called a reduction. We take a problem, we kind of reduce it to another problem that we already know how to solve. And then we kind of use that. So we take our graph, we changed it into a new graph, we solved a problem we already knew how to solve, and then we fixed it back into its original state. This is called a reduction. And it's kind of a way to take problems that you already know how to solve and use them to solve other problems. This kind of ends up showing up a lot in most computer science. We can also define the idea more formally, but that's kind of way beyond the scope of this course. We'll discuss this in more detail later after the midterm. But the idea is you can use problems that you've already solved to solve new problems more easily.